is the last day of classes is Friday of next week, so that's the absolute deadline to present an extra credit if you want to, but it's pretty consistent when I've said who wants to present an extra credit, everyone says, well, I don't. So that's not so relevant to anyone, I don't think. The other thing to note is, so I made this announcement at the beginning, so the multiple of the semester, the multiple choice problems in this, the non-open-ended questions. Those have like due dates, but they don't have deadlines. So if there's any of those that you want to get a better grade on than you currently have, even if it's from like the beginning of the semester, you can. And in fact, probably in doing so, that would be a decent way to prepare for the final exam since that's cumulative anyhow. Cool. All right, so strategy talk over. Let's talk about trig identities. So the next one in the packet is one that we in fact did last time. We did it in a way which, in retrospect, was slightly inefficient. We like took the more complicated side and simplified it down, kind of like what we did there. There is a more efficient way. So I guess the first thing is, would people like to spend time on exactly that identity? Is there a demand for that one? Okay, cool. Let's jump right over. So here's the identity. Tangent z plus cotangent z is equal to secant z times cosecant z. I know it's much more American to say z instead of z. I'm doing so intentionally here because I feel like there's some risk of z being pronounced as c. Okay, so there's an identity. Let's try to give it a proof, and maybe I'll give you all two options for how to begin. You can do it, and I can wait and then we can come together and talk, or you can tell me steps to take in the moment. So people are already quiet for a bit? Okay, cool. Then I will, unless anyone does not have an idea of where to begin. Awesome. I absolutely have no objections to you coordinating with each other and collaborating if you want. I suppose those of you who are a little bit on the isolated side, if you want to move, you can. Any of you all have interest in coordinating with other people? Okay. Making sure everyone who wants it has the opportunity. Right, my mindset is the university has lifted the mask mandates.
Oh, yes, that is. It has to do with it. So, one of them is going to so, right. Oh, yeah.
And so, but then you also have the top.
Yes.
Yes. And I'm like, no, that's
Cool. So there was that nice peak in conversation and then it declined. So I feel like most people are probably feeling pretty good.
Getting there.
Okay. Well, getting there then maybe I'll pause, hold off for another minute or so.
So close. Oh, close is. Oh, we want. That's what it's like. It's not doing part-time sign. Oh, okay. Oh, I see. Okay, yeah, that's like what I see. Yeah. And then multiply. I think it's like C or C.
Cool. Should we talk about it? So, maybe I'll start with this. So there's like the two reasonable things to do. You pick the more complicated side and simplify it. You take both sides at once. I picked people picked one side and simplified it. And many people took the whole thing at once. Cool. Which one should we do? Pick a side. All right. Which side should we pick? Which side did you pick? Tangent plus cotangent. Let's study that. So maybe we'll even go through this proof multiple times. Tangent z plus cotangent z. I'm going to try to give myself some extra space off to the side, so I'm going to be efficient. All right. What did you do to that side to simplify it? And in terms of sine and cosine? Right. If there's nothing obvious to do, that's always a viable thing to do. Tangent is sine over cosine. Okay. No. All right. So now that you've rewritten the sine and cosine, what should you do next?
Find a common denominator.
Seems reasonable. I see two fractions being added. Anyone do anything other than get a common denominator at this stage? Fair enough. That's not saying that like getting a common denominator is the only possible move, but it certainly is the obvious one. So I guess the common denominator will be sine times cosine. All right, so I guess this will be sine squared over cosine times sine. And in fact, as long as we're getting a common denominator, would anyone object to adding fractions in the same step? Yeah, we already know what's going to happen. It's not too complicated this time. By getting a common denominator and adding. Cool. So how many people's write-up have I basically followed on the nose so far? Cool. What's the next step anyone did?
Use Pythagorean identity.
I see a sine squared plus a cosine squared. Pythagoras tells me something. By Pythagorean identity. So by the Pythagorean identity, what does this become?
1 over cosine
All right, so that suddenly is quite, well, that's where we are. And let's take a look at where we want to get. We want to get to secant times cosecant. Are we basically there? Yeah, because what is 1 over cosine times 1 over sine? Well, what's 1 over cosine? Secant. And what's 1 over sine? Cosecant. So I guess the next line would be we write as secant and cosecant and go down. Anyone have any drastically different proofs that they used? Okay. Equals secant z cosecant z by rewriting in terms of secant and cosecant. Cool. I guess maybe a bigger thing to say is how many people in their write-up didn't actually write any words describing the steps? Okay, cool. You're not doing that on the actual thing that I'm going to collect, right? Okay. That's good because I want to see the words. Okay. So, carrying on. Let's do more. All right, here's a claimed identity. Sine squared divided by 1 plus cosine is equal to 1 minus cosine. And, well, in looking at that, what sort of philosophy would you, if you just saw this, want to follow to do it? Like, is this screen to you look at both sides at once, or look at one side and simplify? Cool. So let's try just one side, and we'll see what happens. So, I guess the one side is this side. So let's start with that side. Sine squared phi divided by 1 plus cosine phi is the thing that we want to study. All right. So in looking at that, and possibly also looking at what our target is, what would you want to do to this to simplify? Or maybe not to simplify, because I don't really see any simplification. Let's complexify it first and then simplify in a different way. So what's it that I want to turn the right-hand side into? 1 plus cosine? And I can make the left side look more like 1 plus cosine by multiplying it by 1 plus cosine, right? But if I multiply by a thing, I have to divide by a thing. So here's a motivation for a force step. I'm not saying this is the only possible force step. Let's multiply and divide by, nope, 1 minus cosine of phi. It's hard, I can't actually see what I'm talking about. So let's multiply and divide by the thing on the right-hand side, just because I didn't see anything else. There was another option that maybe we could do this another way as well. 1 minus cosine phi divided by 1 minus cosine phi by multiplying and dividing by 1 minus cosine. Quiz. Sine squared phi over 1 plus cosine phi is equal to that. All right, so there's a thing. And I think that this term, like I want to leave that term alone because that's the term that I want to like survive to the end. In a perfect world, everything else would like reduce to 1. So let's just try to reduce everything else in sight. Cool. So what should we do next? Just try to find a move to make. So let's look at the whole, like I want to leave that thing solved with the blue 11. So maybe I'll even leave the whole numerator 11. I don't want to like distribute the sine squared through it because that would make it harder to see the 1 minus cosine. In the denominator though, I see a thing times a thing. Let's multiply those things out. Maybe we'll see something nice. Equal to sine squared phi times 1 minus cosine phi all over, and then I'll FOIL out the bottom. So 1 times 1 is 1, minus cosine, plus cosine, minus cosine squared. All right. Anyone see a thing? What do you see?
The denominator will become sine squared.
The denominator is sine squared. So let's use that. So since 1 minus cosine squared phi equals sine squared phi, or if you like, that's by the Pythagorean identity. But you know that works. This is sine squared phi, 1 minus cosine phi, all over sine squared phi. Anything useful to do with this? You can cancel. Oh, hey, is that what we wanted to get? So if you like, the first step here was like a blind faith step. I know these two things should be the same if this identity is to be trusted. I could have gotten more confidence by graphing. So I just put the thing that I wanted to see there, but I needed to keep it equal, so I had to divide by a 2. How many people would have been tempted to instead like try adding and subtracting the thing to the other side? You could. Presumably that strategy would still have worked. Yeah.
Could I just use the trig identity for sine squared, like right at the beginning, to just make it 1 minus cosine squared?
Awesome. Yeah, there's a slicker way. So let's start with, so sine squared phi over 1 plus cosine phi I guess I don't have space to write the logs, but using the Pythagorean identity, what did you rewrite that as?
I just made it 1 minus cosine squared over 1 plus cosine.
Cool. And that's by the Pythagorean identity, but I put myself in the corner so I don't have space. Nice. What did you do after that?
Well, and then just cos negative cosine squared divided by cosine would just be negative cosine. Or does that not work?
So you can only cancel something from the numerator and denominator if everything in the numerator and everything in the denominator is multiplied by it.
Okay.
So you can't do that. There's a thing that you can do. Yeah.
Could you cross multiply and FOIL and then you know the Pythagorean identity is true? It would justify it. Because you would get 1 minus cosine squared equals sine.
Yeah. So here's yet another proof technique, which I'm going to hold on to this one and then start another proof also. So let's find out what that would do. So that would be starting with the whole equation.
Yes.
So sine squared phi divided by 1 plus cosine phi equals 1 minus cosine phi becomes sine squared phi equals 1 minus cosine phi 1 plus cosine phi by cross multiplying. And I'm okay with both of these being up at the same time because I'm going to do opposite steps in both of these. So in what you have here, you have a difference of squares. So we can use the difference of squares formula to do something. Let's see what it gives us. And then hopefully we'll see a cancellation too. Equals 1 minus cosine phi 1 plus cosine phi. So now do you see everything multiplied by something in the numerator and then everything multiplied by that same something in the denominator? Yeah, there's how you can do that cancellation. Yeah.
I guess it's kind of a cheesy way to do it, but if you go back to that sine squared over 1 plus cosine, and then if you can recognize that 1 minus cosine squared is equal to sine squared, then you can kind of just finish it there, because it would be the same to each other. Like the
one on top of it right here.
the one right there, not that one, the one above it.
Okay.
No, not that one. The one right above that one you were pointing at.
Oh, yeah, so you could go right here and say, I know that sine squared is equal to 1 minus cosine squared. So you can replace this by 1 minus cosine squared, 1 minus cosine, 1 minus cosine squared, and do the canceling.
Yeah.
Which I guess is roughly what happened here, too. Yeah, so I think I would call that cheatsy, I'm not sure what word you use. I would call it a fine proof strategy. I think it's roughly the same as this one, but doing the opposite replacement.
Okay. Yeah.
Cool. Should we finish up the cross multiplying strategy at the top, or are people happy? Cool. Yeah, many, many ways to do the thing. Cool. All right. So, a thing to remember when thinking about trig identities is once you know a trig identity, to some extent you can forget why it's true and just remember that you know that trig identity is true. And so as you build up more and more, you'll have a library of things you've already done, and you don't need to redo them every time you need to use them. Once you know a trig identity is true, you can use it. Let's use that philosophy to do this next one. So this next one will be 2 lines. Get that. Here's an identity. Tangent plus cotangent over secant times cosecant is equal to 1. I thought that item 8 from this document will be useful. So, yeah.
You would just cross multiply and because we know that tangent theta plus cotangent theta equals secant theta or times cosecant theta is the same or probably. We're done.
Okay, that was a lot, and that was the amount of time it took me to write the whole step. So, cross multiplying gives us that. And what does item 8 say?
x equal to the dime.
Yeah, well.
Yeah.
But
That,
those two things
they're
are
equal
equal.
to, yeah.
So in particular, this is just already true. This is true by item 8. So you took an identity you wanted to prove, you reduced it to something you knew was already true, so you're done. So if you can remember previous trig identities you've proven, you can save yourself some effort. Presumably what otherwise you'd wind up doing is repeating the proof of item 8 right here, so you would have some extra lines and some redundancy in your work. Nice. Cool. So on the next page, I think there are two that are not necessarily more complicated. They're just use ingredients that we haven't used yet in this packet. So here is an item I claim is true. I claim that sine minus cosine quantity squared is equal to 1 minus the sine of 2x. Cool. So there's an identity to be proven. What would you want? Well, maybe I'll give you guys a chance. I can be quiet for a bit and you can just do it and we can talk together. So people out there be quiet for a bit and give you some time to think. All right. Does anyone not see a starting move to make? Okay, then I will be quiet. Pause and just see if there's anyone who doesn't carry previous notes on them. Does anyone not remember the double angle formula for sine? Do you have an internet connected device on you? It's on the internet. So if yours, I'm not even going to look at it for you. That's your phone. Double angle formula sine. That's not something you can do on like an exam. But really, it's more practical to know like that a fact exists and be able to find that fact instead of trying to keep all of the facts that you could possibly ever use in your head at once. Cool. So what's the sine of 2x?
Oh, sine of 2x is it 2 sine x cosine x? So it'll be 1 minus that.
So there's,
All right, okay.
anyone feel, as people, is anyone feeling stuck at where they are right now and not sure where to proceed? Okay, tell me where you are. You have made an error in how you prioritize. You have forgotten the point. Was that the same across the road?
Yes.
Oh, okay. Awesome.
Yeah, I just lost it.
Yeah.
Cool. So I see, like, you've done some stuff with the left hand. I guess the theta should be x's too, right? But that's not the main thing.
I just this is just a formula. I just wrote that down.
Okay. The thetas and the x's should be the same over here.
Oh, I don't know why I wrote that.
I mean, that's fine. I'm using the data. Cool. So here's the left-hand side. What would you want to do with that? That seems reasonable. What are you going to plan? It's not a, so the difference is squares. We go with one more plus one more. On the left hand side, you're missing a column.
Okay, this is very interesting. So, I found out sine squared minus 2 sine
That was it.
Yeah.
So just to touch base, seeing how people are doing, has anyone already completed all of the actual identities in the whole document at this point? Okay, here's an opportunity for you if you would like. There's an extra credit thing on the next side. If you want to work on that, and if you want to do that, that's an option. But maybe right now, so are people feeling pretty okay to talk about this one anyway?
Yeah.
Cool. Let's talk through it. So, right, on the one hand, there are like a half dozen ways we can begin. So I guess like first thing to decide is take a side that looks more complicated and simplify, or look at the whole equation. Whole equation? Pick one side and simplify? Okay, I think the pick one sides have it. I suspect that the argument will be very much similar to the use both sides. Nice. So, which side would you want to start with to do stuff? Seems reasonable. So let's look at sine of x minus cosine of x squared and do some stuff with it. So what did you do to that first? Boil it out. So boiling, depending on how comfortable you feel with, well, no, I saw enough errors, but let's do the foiling in many details. So that's sine x minus cosine x. And to some extent, like, I set you up to make this mistake because a lot of other times we, did something similar, but too quickly, I think. So there's that by what squared means. That's right, all I did there is use what does it mean to square and multiply by itself. And now we can FOIL. So FOILing, you do forced sine squared of x. Outside, minus sine x cosine x. Inside, minus cosine x sine x plus cosine squared x by FOILing. All right. Cool, cool. And you probably did another step that in this one step, right? Because the two terms in the middle are the exact same term twice in a row, so it's just minus 2 times the middle term. So I think I won't even give a horrible description for that. Sine squared x minus 2 sine x cosine x plus cosine squared x. So how many people in FOILing would have jumped straight to that bottom line anyway? Yeah, that's fair. On the other hand, that's an easy way to make the common mistake that was made by doing too many things at once. Cool. So there's that. What next? Yeah.
Using the Pythagorean identity, I rewrote sine squared x as 1
Oh, cool. Yeah, we could do that. Is sine squared x minus cosine squared x minus 2 sine x cosine x plus cosine squared x by Pythagoras. All right. What next? Oh, is there a minus that should be a plus?
Yeah, an extra cosine.
Oh, yeah. There's a sign that should be a 1.
Yeah.
All right, so maybe for emphasis there, I put the parentheses in. That's the new term that here. Okay, now, is there anything that cancels? There's a minus cosine squared and a plus cosine squared. All right, and finally? Or the double angle identity. Yeah.
We did a little differently. So
Yeah.
for you have it in it's like the third line down, the sine squared x minus right there. Couldn't you just already add sine squared x and that'd be 1 and then 1 minus, yeah, that's it, okay.
Yeah, you could say, sine squared plus cosine squared is 1. But
Just
second,
jump to
then
that.
you could have dropped it down to there. Anyone do anything else different? I mean, I know people did, because there's lots of people doing stuff, but I guess stuff we want to talk about that was different. Cool. Groovy. So, there's 1 minute left on the clock. This last identity, well, I said this page was the more difficult one, but that really was the only one that uses anything new. This last one is, in some sense, more of the same. If you want to see this in a while, let's just talk through general ideas without writing. What would you want to do for that to start the process?
Split it in terms of sine cosine.
But in terms of sine cosine, and maybe that would be starting with one side and doing that, but maybe you could take the whole thing. We went in terms of sine and cosine. Hopefully some stuff would cancel, maybe it wouldn't. I guess you see a fraction, well, difference of fractions on this side, a single fraction on that side. Simplify the fractions. Maybe you have to cross multiply, maybe not. Cool. So, as for my comment, on the next page in the notes, you will see an extra credit. in which I point out that this philosophy of using old identities to get new identities isn't something that's limited to trig functions. Here are some identities that I claim are true, but absolutely really infinite. Who are these? Get an argument? Come training. If you want the extra credit. You have until Friday of next week. Cool. Oh, yeah, the change of base formula says that you don't need to care about that base actually. That one's flying. That's nice. That looks like an idea.
Alrighty, I'll see you guys soon.
Can you go over how we can tell how you see CRX?
Yeah.
I just can't seem to figure it out.
Maybe it's useful to even like see pictures of things. So the times when there might there's a weird ambiguity for side-to-side angle triangle. So let's. So, I think it's useful to even do something we haven't done before. Let's actually draw a picture of this situation. So I see right here a line of length 5. So we try to find something like scale. Here's 5 units long. Then this next line is length 2. I don't know what direction it points in, so I'll just draw a circle of radius 2. That other line could be any of these lines. I pretend that's small. Then I have an angle of 15 degrees sitting here. And how many times does it look like this line crosses that circle? So if I use this focal line, do I have these numbers correct?
Yeah.
If I use the ones line, do I have the numbers correct?
Yeah.
So there's the idea of why there should be two of them. But let's talk about where that comes from in the law of sines. So the law of sines says that you have some angle, you use a definite missing angle. So you would say, well, I know that the sine of this missing angle divided by 5 is the same as the sine of 15 degrees over 2. So you go and solve that with sine of alpha. And you could compute what that number is using the machine. It's less than 1, I hope. And so now when you think about this angle alpha, you know it's sine. You know that that angle alpha has to be between 0 and 180 degrees. And there are two angles that give you a thing that that's sine in that between 0 and 180 degrees. So like the rule that we gave only arrays. This was the longest side of the triangle. So that means this angle also might be obtuse. So inverse sine would give you an acute choice. The other one will give you the obtuse choice. So the thing to ask yourself is, and in this case, the answer is yes. So alpha could be obtuse. I guess we could vary this triangle, this picture, and see other reasons why that should be. So let's take the same one, and just imagine instead of this being 5, this was 1. So in that case, you'd have the same angle. Oh, that's not going to be parallel, is it? So if you go forward, how many times does this green line cross the circle?
1.
Just 1. So it looks like there's only one choice there. If this side length 5 were much bigger, it would probably do. How many times does this really come across the circle? 0. So this is why sometimes there are no solutions.
Okay.
But the easiest way to detect it is just ask yourself about this side. Is it the longest side? If it is, then there might be 2 solutions. If it's not the longest side, then there's definitely not.
Okay.
And then you can use this. Asking yourself if that's bigger than 1. If it is bigger than 1, then there can't be any solutions. That's this case.
Okay.
Yeah.
Okay. Just wait till
Yeah.
Okay, thanks.
Yeah. Cool. So, well, maybe I should get myself ready somehow. There's still a few minutes though. People have any questions, homeworky or otherwise they'd like to ask about? Yeah. That's it. Which I think you should, right? These are all different angles.
It's just like whenever just it's just the percent of that.
Then that is the problem. So you took percent time away. And you got that decimal process. You're saying calculating something.
Yeah.
And you were making out of doing that. If you are going to do motion, there's something wrong.
Yeah, that is.
If you end up doing that, then there's a problem.
Okay. Yeah. I just wanted to double check that. But that is
Yeah, do the same check again, making sure you want to do that. Stop recording.